Okay, I will start the subject by first going through a simplistic version. You know, it's going to be an introductory section to the larger formulation of Feynman path integrals. So it is, title is Propagators in Quantum Mechanics. Okay. Or wave mechanics, really. Let's put the title in a rather low level, wave mechanics. Let me restrict myself to the Schrödinger picture. Schrödinger picture. That is, all the observables are time independent, so is H. My H is time independent. Well, if H is time independent, the time evolution operator, as we have seen before, is H t minus t0. So when you take this and act on it, act by this on the state which you have at time t0, then you get this sign of t. Okay, now let's convert this into the language of wave mechanics. I think he unnecessarily goes through the so what is this? Okay. So how do I go from these expressions, which in the abstract vector space language, to the wave mechanics language? I project this along the x, which will give me the psi of xt. And similarly here, d cube, simply x e to the minus I over h bar h t0 psi of t0. Well, I haven't done much. All I have done is really to go from the abstract Hilbert space notation to wave mechanics notation in the left, but notice that I couldn't have done it yet in the right-hand side. I could do it in the following manner. Let me go as straightforwardly as possible, by inserting here a completeness identity. To have the general form at hand, and then I will introduce a few more things to go to the wave mechanics, simple discussion of wave mechanics first. But here, so what do I have then? I have the following: psi of xt is equal to d cube x prime x e to the minus I over h bar h t minus t0 x prime psi of t0. You say, well, we haven't achieved much, seemingly. But if you say, give this a name, then elaborate. Call this k xt x prime t prime, and this one is now psi of x prime t0. The notation is not symmetrical, aesthetic-wise, not that good, And Sakurai also complains along the way and he shifts notation. But let me not worry about the notation first. And then let me write the equation I obtain. D cube x prime x k that's the non-symmetry in the notation, aesthetics. I'm not talking about anything else. Usually you have to use the pairs x and t and x prime t prime or stuff like that so that they go hand in hand. But we are not doing art, we are doing physics. So let's proceed a little bit with this unaesthetical notation. Well, this is sort of the integrated version of the time evolution equation. Remember, we said if you have an initially specified state, you act on it by a time evolution operator, which is bilocal in time, and then you carry it over to the future, and it gives you the future state. And this is the integral version of it. Notice that this plays the role of that time evolution, because the initial wave function is specified at t0 at point x prime, and then you act on it by that. Integrate over all x primes. Whatever will that mean, we'll see. That's an important thing. And then you get the wave function at a later time. Is there a simple way of obtaining that expression, k? Well, yes, for instance, if we really take this and do a bit of manipulation, what do I mean? I mean the following. Take that k with all those entries in here, and the explicit expression is giving there k, x, e to the minus I over h bar, h, t minus t0. I'm leaving some space, obviously. I'm going to insert identities. When you leave space, you are going to insert identities. What is the right identities that you have to insert? Well, for instance, as the Hamiltonian appears, Hamiltonian is the generator of time translations. So if I somehow insert energy eigenstates, then these operators may be converted into energy eigenvalues, right? So how do I do in an elegant way? That's the problem. Now let me do it in the following manner. Now I'm worried about the elegance. I would like to insert identity here. What is that identity? That could be 1 EI EI. Obviously, Hamiltonian being a Hermitian operator, the most important of all the physical operators. Then it's complete and orthonormal. E denotes the energy. It's my invention. I don't think it's the best notation or not. Energy eigenvalues are to be labeled by the E's, obviously. And insert another identity in here to distinguish them. Let me use a different index, J. EJ, EJ, that's also an identity, the same completeness, but labeled with different indices. So what do I get? I get the following: sum over I and j, x EI, EI, e to the minus I over h bar, h, t minus T0, EJ, EJ, x prime. Let me leave the first and last factor, but focus on this. These are the E's are defined in the following manner. Let me remind you the definition of the energy eigenvalue equations, EI, EI. In line with the usual notation we have been using from the beginning. So then this picks J and then becomes a number. You move it out of the E expectation value. It's not an operator, it's a number. EI, EJ, as is the case for all the eigenvectors of Hermitian, operators, I assume, without losing any generality, for the sake of elegance in notation, discrete, I could have used the continuous spectrum without any problem. Then I carry out one of the summations. Then I get K sum over I x ei e to the minus I over h bar ei t minus t0 and e j x prime. Notice that in our convention, E energy eigenstates are the states that we have chosen, and we have considered their coordinates in the x basis. So this is psi ei of x, and this one is psi ej star of x prime. So, oh sorry, i's. I have carried out the summation. Sorry, so there's single sum. So what do I have then? I have the following. I psi ei of x, or star and x prime. Let's put it first. Psi ei of x e to the minus I over h bar ei t minus t0 is the k, which we have denoted as x t x prime and t0. So, a little later I will change the notation, and you'll see that notation will be more educative in that sense. But this is a representation of that k in terms of the energy eigenfunctions. I could have used any other set of eigenfunctions. You know, notice that here I inserted these complete identities in terms of energy eigenfunctions. I could have inserted the momentum eigenvectors. Well, inserting momentum eigenvectors will be as useful as this one, because if I am considering a free particle, h is p squared over 2m, therefore h and p commute. That's a general phenomenon. For free particles, Hamiltonian and the momentum operators commute. That also is valid for the relativistic case. Remember, it's not only non-relativistically. So therefore, it could have also given me a nice representation. It's energy or momentum. Well, we have already used x, so these are the options. What does it tell us? It tells us that if I can construct this k through this recipe, this is an expansion recipe, then I can use it in the above expression, this one, which is the wave mechanics version of the integrated time evolution, and construct a psi. But summation over all x primes, that's something which we have to keep in our mind. That's a very subtle issue. So what are the properties that I can get from here? By the way, you may wish to construct this explicitly for the free particle. Let's construct this for the free particle as a first step, and then I will study properties. For example, what is the equation of motion k satisfy? What is the expression for k when t goes to t0? But these are the important mathematical properties related to physics, of course. But what is the explicit form of it for the free particle? How do I construct this for the free particle case? We remember, first of all, that the first observation, I invite you always to really go through this identification of compatible set of commuting operators when you are doing a physics problem. It's a free particle h, which is p squared over 2m. Obviously, it commutes with the p. Therefore, these eigenfunctions which I have used in there explicitly are really also common eigenfunctions of the momentum. Furthermore, as the spectrum is continuous now for the free particle, that's first property. Second, spectrum is continuous. We have already studied those things. Continuous. Therefore, I have to replace the discrete sums in there with the continuous sums, which are integrals. And I can use E or P interchangeably because I know that they have the common set of eigenfunctions. What are these common set of eigenfunctions? They are psi p now, labeled by. And if I use a certain normalization prescription, when it comes to free particles, remember we have discussed that in detail. There is an ambiguity in the definition of the normalization because they are not normalized in the strict sense. When you get the explicit wave function, take the mod squared, it is constant. When you integrate overall space, it's infinite. So we had to develop a certain recipe. Well, the recipe is to take them as the momentum eigenvectors, and so use the delta function normalization prescription, split the points. Instead of taking psi of x squared and integral over, then we say split the points and write the right-hand side not as 1, delta cube of p minus p prime. So then the normalization is this. This is the common eigenfunctions of the energy and the momentum for the free particle case. So what is the expression? First I have to modify this to convert into the continuous language from the discrete language, because free particle is continuous spectrum. So it becomes, now I will afford to use a symmetric language. I will choose the language to be symmetrical. That is, I will take this one t prime, or I could have taken this x0, depending on the taste. Let's take it to be x0, for instance, to make it more aesthetical. So, k, xt, x0, t0, b cube p, the discrete sum over I is converted into a continuous sum, c, psi star, p, x prime, psi p, x, e to the minus I over h bar, e, well, from this point on, if you want, put the p in here, t minus t0. You don't really have to do that. So it is this expression. What is it? 1 over 2 pi h bar to 3, because each of them has 1 over 2 pi h bar to the 3 halves. And this one is I over h bar p x minus x0. So we are, for the sake of aesthetics, we don't want to ruin the entire thing, right? Okay. This and plus or minus I over h bar p squared over 2m t minus t0. Ah, nice. Something which we can really finish and get a propagator expression. Eventually, this is going to be a good testing ground because we will try to reconstruct this using a honest to goodness formal version of Feynman's path integral. But this is really a nice thing that which we can handle easily. So what do I mean? I mean the following. It is a polynomial in P. Let me rewrite it in the following fashion. d cube P divided by 2 pi h bar cube exponential, it's more comfortable to write it this way, exponential the following, minus I t minus t0 divided by 2m h bar. I have p squared. I'm using the trick of completing the full square, right? You are by now quite familiar. So if you have to multiply with the inverse of this, so minus 2m over t, I over h bar is common, so there's no problem, 2m over t minus t0, x minus x0 times p. For aesthetics reasons, let me write it as such. So you see how do I complete this into full square? I write this as p minus m x minus x0 divided by t minus t0. Ah, you say, oh yeah, this must be it, because it is something that you recognize, right? Because x divided by t is velocity times mass is momentum. So you have done it correct, so that momentum minus something like a momentum squared. Well, of course, I have to compensate by the missing term. What is the missing term? There is a plus of this. I have to subtract the minus of this. M squared x minus x0 squared divided by t minus t naught squared. Nice? Okay, so what else? What else is the following? Notice that this is a momentum integral. This extra piece, which is of course multiplied by that initial factor, I will write it. It doesn't involve p. I will take it out of the integral. So that thing is what? First of all, let me write this cube down here. And what is left over in here? First of all, the sign is plus. And then there is m divided by m. Nice. So it is I over h bar 1 over 2m x minus x0 squared divided by t minus t0. How nice. Well, it's really, when you're playing with these simple problems, you really enjoy it, because things are so simple, but beautifully simple. What is left over, this comes out as it is. The remaining is d cube p e to the minus I t minus t naught divided by 2mh bar p minus something. Can we afford to be using that ambiguous language, something? Yes, because the integrals of the p is from minus infinity to plus infinity. It covers the entire spectrum in my x direction, py direction, pz direction. So if I redefine this, call this q. P minus something which doesn't involve p is called the q. So d cube q is the same as d cube p. So the integral is d cube q e to the minus alpha q squared. What is alpha? Let me write next to it. Alpha is I times t minus t0 divided by 2mh bar. How nice. That is what I have defined as alpha. Notice that this is a Gaussian integral in three directions, in the dqx, dqy, dqz, and they are factorized form. So this has the pi over alpha cube. Remember, I told you that this integral must be a part of your culture when you are taking quantum mechanics. The Gaussian integrals are supposed to be known by heart. So we are there really. So what is it? E to the I over h bar 1 over 2 m x minus x0 squared divided by t minus t0 times I will erase this. You have copied it because I don't want to ruin the picture. Well, when the course is recorded, you have to be careful in using the board. So what is left over? There is pi over alpha cube in here, 2 pi h bar cube in there, and alpha is that complicated expression. Okay. So, and I will handle this. So it is some number times exponential of I over h bar something. This is usually denoted as d, t and t0, the usual notation. Sometimes some people prefer to call it 1 over d. That's a notation to write it symbolically. So what is it? It is the following. E to the I over h bar s classical xt x0 t0. You say what? Kemal, that's where the Lagrangian is coming in, you know? Kemal always wondered, why Hamiltonian? Lagrangian is so important in classical mechanics. Why we don't have any physical use of it? You see, we are moving there. Divided by d. Notice that it's only a function of t minus t0, really, beautifully. Let me work it out explicitly now. First, let me demonstrate that the exponent contains really the classical action or the time integral of the classical Lagrangian from t to t0. And the second, what is that d? So the first step is, what is S classical for t0 to t, dt prime L x and x dot, right? That's the classical Lagrangian, and its time integral is the classical action. Let's, for the problem in hand, let's compute that. What is the Lagrangian, classical Lagrangian that is? Well, it's important to use these labels because what I'm doing is classical now. 1 over 2m x dot squared minus v of x. But v of x is 0, right? We are doing free particle. So it is 1/2 mx dot squared. And for the free particle case, this is a reverse logic. But I will go to the direct logic of Feynman in a moment. I am trying to construct the propagator using the known results from the conventional canonical place. So in that sense, this doesn't have too much of value, right? Converting one information to the other cannot be considered that big an achievement. I will give you we will start doing it this morning and we'll continue in the afternoon. So it is this one. For the free particle, the equation of motion of any kind, from Newton to Lagrange or Hamilton or Poisson, tells you that v is a constant, right? dp dt is equal to 0, so p is equal to constant. M times v is a constant. V is a constant. That's what? 1/2 mv squared. That's the Lagrangian, and v is a constant. We put the vector on it, right? So how do you integrate this? Integrate dx dt is a constant. What is the constant value? The constant value is the value at t0, right? This is the one. So you get x of t is v0 t0, v0 t, sorry, plus another constant. That constant is obtained by setting t equals 0. That gives you the x0. Okay, so I'm really in there. What is it? X at t minus x at t equals 0 is equal to v0 t. By the way, I am taking now t0 is equal to 0, the origin. I may not have it, so it would be v0 at t equals 0. So what is the classical, how do you integrate this? This integral is done as it is 1/2 m times the v squared. It's a constant, you take it out. M v squared times t minus t0. Okay. So if you want, you can substitute the v as x times x0 divided by t times t0, which is the case, right? xt minus x of t0 divided by t of t0, taking advantage of the constancy. So you have 1/2 mx minus x0 squared divided by t minus t0. Indeed, the first part is demonstrated. E to the I over h bar s classical. Classical action is the time integral of the classical Lagrangian. Actually, that is what Feynman has noticed when he was preparing his PhD thesis in late 40s at Princeton under John Wheeler's direction. He has seen this statement, cursory statement in Dirac's famous book. I don't know whether any of you have seen that Dirac's famous book, Principles of Quantum Mechanics. He said there must be some relationship between quantum probabilities and e to the I over h bar, the classical action. Some relationship between transition probabilities. Well, he wondered, that relationship is a proportionality or equality or what? S classical versus the transition amplitude, which I will turn my attention. That's K really, formally. But anyway, that is that expression. And what is the D? Let me finish the computation of D. I write the D in the denominator, therefore it must be D minus the inverse is pi 3/2 up there, alpha to the minus 3/2 there, and 2 pi h bar cube. The importance factor is alpha. Alpha to the minus 3/2 is I t t0 2m h bar minus 3/2. Or let me put it upside down. So, yes. Well, perhaps just 2m h bar divided by I t minus t0 3/2. That's alpha to the minus 3/2. So if I now try to squeeze that in, the inverse is, you move the pi in, put it next here. So 2m pi h bar moved in. And there is this factor down there. So first of all, I t minus t0 3/2 times 1 over 2 pi h bar cube. There is a 2 pi h bar 3/2 in here. Notice this one. And if I cancel that, I'm using my eraser, just these. Put the 3/2 in here. So therefore, finally, I have the following expression. M divided by 2 pi h bar I t minus t0 3/2. So let me write this result cleanly in here before we turn our attention to a more advanced discussion. These are sort of, notice that this is not really a derivation. We have used an already known result from the canonical version, substituted in the representation that we have obtained for the K, and we are getting an explicit expression for the K. So K is M 2 pi h bar I t t0, this is not 3/2, times e to the I over h bar, h classical xt, x0 t0 is the result of this K. So you can use this for really finding any future value of the wave function if you know the initial value. It's a simple thing. And you may say, okay, it's some kind of achievement. Notice that it's this factor In more advanced discussions in field theory, this is the so-called determinantal factor. It's important. It depends on t minus t0 in this fashion. 2 pi h bar is h itself. It's proportional to the mass, and it behaves m to the 3 halves with the mass. The more massive the m, the larger the k. When t approaches t0, and this, of course, should have a certain behavior. So what is the behavior really when it approaches, t approaches t0? So what is the behavior of the k? It's proportional to e to the I over h bar m over 2, sorry, let me write it more aesthetically, mx minus x0 squared times 1 over t minus t0 divided by a factor, some factors, and t minus t0 3 halves. Notice that there are here x minus x0, x and y minus y in components. So it is the product of 3 exponentials really, if you expand this as x1 minus x0 1, x2 minus x0 2. And what about the following expression? E to the alpha divided by t0, t minus t0, divided by t minus t0. For all, because there are 3 factors, you can multiply this as 3 factors. This is, what is this factor? This is x1 minus x0 squared, for instance. Then limit t goes to t0. It's going to go to the dq. Well, first of all, this first factor goes to d x1 minus x1 0. And there are factors of that because there's y minus y1 0, z minus z1 0. If you put them all together, put all together there. This first factor is that one, but then you have everything. So if the claim is the following. We have obtained the explicit expression, and using that explicit expression, we are claiming that xt, x0, t0 goes to, when t goes to t0, it goes to delta cube x minus x0. Which is, if you're familiar with those exponential representations of the delta, which I don't think so, that even I never had the fun with them in the past, so you can really prove this condition, but this condition is more easily proven in the formal expression. Let me remind you what formal expression was. As I said, this is more cumbersome, mathematically more involved. But the explicit expression already contains that result. What was the explicit expression? For the continuous spectrum, remember, what did I write? I have written this as x by x0 e to the minus I over h bar e t minus t0, right? It's something which we have erased. Check your notebooks so that we don't make any sign mistake in copying it. This was the expression. What is the expression when t goes to t0? In the right-hand side, I have dqp psi p star x psi p of x0 formally, independent of the details of the explicit expression. What was this? This was x0 p, and this was px. Use the completeness. Isn't that beautiful? When you are using the, can you say it easily? Perhaps you haven't. write it in the following fashion. X0, this is equal to this inside. dq p, 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 x. I have rewritten it so that you can easily see, because these are the expressions, right? When you write it in such a fashion, you see that this is the completeness of the momentum operator eigenvectors, which is 1, leaves you with x0 and x, which is delta cube x0 x. So this formal proof is, of course, rigorous and clean. It's easy. And to see it from the explicit expressions by taking the limits and using delta function representations is more indirect, and you may not be that experienced. So if you want to prove that statement, always refer to the explicit expression that we have constructed for the k. Does it make sense? When t goes to t0, the k goes to, propagator k goes to the delta cube x minus x0, which is an identity operator, right? It tells you that you cannot move from x0. If you don't move in time, if t stays at t0, you don't have to move in space. That x should stay at x0. That's the demonstration. That it's an identity operator practically. So that is sort of the discussion, the simple discussion, which is insightful because it gives you this expression, which was the triggering point of this opening up of this new avenue, formulation of path integral formulation of quantum mechanics, an alternative formulation. He has just noticed this from Dirac, and he has started pushing it, something which was not trivial at the time, that it's a single expression, classical action. In classical mechanics, there are just well-defined classical trajectories, unique trajectories, connecting one point to the other, and those trajectories are the ones which minimize the action. That's Hamilton's principle, right? You know it quite well. The shortest distance between 2 points is a straight line. How do you know? Because that straight line is the one which minimizes the action. The line integral of the Lagrangian. It's beautiful in its own right, and that's some philosophical depth in that principle, Hamilton's or Maupertuis's version. Now we come to quantum mechanics, and we see that there is not a single trajectory possible between any 2 points. There will be infinitely many trajectories. I'll demonstrate. But Feynman asked, how do we know that out of those infinitely many trajectories contributing expression, when you take the h bar goes to 0 limit, that's the one way of going to the classical limit, reduces this to this simple expression? Isn't that a beautiful question to start with? I think the question itself is very profound and beautiful. And when you ask such profound questions, however simple they are, it opens up avenues for new discoveries which eventually bring in Nobel Prizes. So good luck to all of you. Try to ask those simple and profound questions, and eventually you'll see that it leads to something great. So this is a good point to give a break to get really a full start of the actual Feynman's construction.